Hello everyone, I am Ajit Kumar and I have worked under my professor Dr. M. Rajshekhar Babu. Today I am going to give you a presentation on energy conservation approaches for green cloud computing. Uh, this will be the outline of our presentation, abstract introduction related work, compared to studies and conclusion. So let's go into our presentation. So these days, cloud computing has become a very vast usage in our society. Most companies are investing more to construct large data centers to maintain the cloud services. Uh, these data centers have high operating costs and also major amount of carbon rates in the environment. They release a lot of carbon dioxide and other harmful gases. Uh, yeah, these data centers also consume very large amount of energies and also very complex in their infrastructures. So we need to think of some green solutions to reduce this effect of harmful gases in our environment. So in this presentation, I have presented various works done by other researchers to make green cloud computing and make the computing more efficient and reduce the amount of carbon dioxide in our environment. So we have also discussed the main concepts of virtualization, which is a very important concept in reducing harmful gases effect in our environment, and also numerous approaches that use virtual machine scheduling and migrations that can help in making system more efficient, and thus we can save more energy. Coming to our introduction, uh, cloud computing is it's one of the most developing technologies in these days. So cloud services offer software, accessing data and data storage services, and computation through the internet, and the clients are charged only for the amount that they have used the cloud services. So it's a very developing technology these days. So however, for this increasing demands of the clients, the companies need to construct very large data centers. But these data centers consume a lot of power, and also from a survey we have known that in 2012 that the total power consumed by the data centers is approximately equal to 38 gigawatts, and compared to the power consumed in 2011, the total power is 63% more than it's consumed in 2011. So that's a very huge amount of data consumed. And also even the servers are not working. They must be switched on for 24 hours a day because of the cloud services, and if they're switched off, and we can't work with them. So it's a lot of power wastage, as they are on for 24 hours and they are not used for some time. And according to the other statistics, uh, till the year 2012, the total data centers have used up 30 billion watts of power, and this can be produced by 30 nuclear power plants. And we can save some energy by the companies can save some energy, like by solar and wind energy, so they can produce their own plants, own power plants, and so that they can use the power produced from the plant. So this is a very good method. Large data centers can use this type of method, but small and other companies can't use this. So we have a lot of power wastage there. And so green computing, it's a very environmental and friendly computing. It brings to maximize the efforts of utilization of power consumption, energy and efficiency, to reduce the cost of servers and also the carbon dioxide emission. So the main objective of green computing is to inspect the present computing systems, and they tend to reduce the cost and reduce the energy consumption, so that it will be very useful for the our upcoming future generations. And we have some stats here. The total amount of energy consumed by one Google search is equal to the carbon dioxide that one human breathes out in 3 seconds. And the amount of carbon dioxide emitted by Google search in 1 month is equal to that of humans breathe in 824 years. and this carbon dioxide is declining our environment and with the greenhouse effect. So there's a need to take cautious actions to reduce the harmful gases and protect our environment. So we have some software solutions through virtualization. It's a very uh, privileged technology is used these days to reduce the energy consumption, and virtualization can be used to better resource isolation and can decrease the infrastructure energy consumption through resource association and live migration. The best possible way for improving energy efficiency and power consumption is to adopt virtualization techniques to get better resource isolation. Also, using virtualization techniques, many energy-aware resource allocation strategies and scheduling procedures are proposed to optimize total energy consumption in cloud environments. So, this figure we can see with one Google search, we could generate as much as CO2 as human breathe in 3 seconds, and it could power a 100-watt light for 11 seconds. It could consume the same energy as human burns in 10 seconds. So these are all the stats. We also see the Google search in 1 month. It's equal to CO2 emitted by a human in 824 years, and it could also power a 100-watt light for 4534 years. And these are the other stats. So we'll go into the related work. We'll see some works done by researchers previously. So Lee and Zomaya proposed an energy model for of a cloud task for creating energy aware task association algorithms. This is to decrease the energy consumption in cloud administrations. However, this the energy model merely assumes the connections between CPU utilization and energy usage is with linearly expanding. This their energy model is developed on the basis of processor usage has a straight connection with the energy consumption, and Jung mainly focused on power consumption by the physical hosts. Their energy utilization models do not consider the effects of particular workloads running on specific hardware equipment. From their work, they presented a Mistral. A Mistral is nothing but a comprehensive controller frame that optimizes power intake and consumption, and performance assistance and the monetary expenses sustained by various adjustments, and controller itself to amplify the overall utility. Mistral can deal with multiple distributed applications and large-scale infrastructures through a multi-level adapting order and accessible optimizing algorithm. So Chen proposed a linear power model that shows the behavior and power consumption from discrete components to a particular work node. In their experiments, the VMs are configured to have distinctive number of vCPUs. They outlined the performance, power consumed, to power efficiency and the total energy of the VMs by varying the number of variables that are used in benchmarks. The output shows that virtualization brings in overall performance deprivation with respect to these benchmarks. Still, this deprivation highly relies on situation, and there ought to be no effect for pure user code. So Stewart and Shen, these two discussed on how to improve the and maximize the green energy to use in data centers. They modeled a data center which receives power from discontinuous wind renewables. Their results mainly highlight the challenges in dealing with an uncontrollable power resource that is irregularly unavailable. Their work summarizes a research plan for controlling the renewables in the data centers. Their work substantiates the current efforts to incorporate renewable into the framework. So we'll see some comparative studies, and we'll compare the graphs and the values of power and time. So the response times with Mistral are fairly higher than compared to the other various methodologies, and it marginally interrupts the performance objective when demand rates crest, as it utilizes at most 3 hosts out of the 4 to save power. Uh, However, because of high frequent and rigorous adaptations in various approaches, performance interrupts the performance power, and rigorous adaptations and power costs occur more frequently than with the Mistral. Particularly, the response time with the performance power vary and after that stay high as it performs numerous adaptations. than Mistral. Power cost is compelled to perform migrations during the peak request rates to meet the capacity variables, since it does not exchange between performance and cost like Mistrals. So from this graph you can see that the performance power and the power cost is plotted here with response time and the times taken. And you may see here that performance power indicates the trade-off between performance and power consumption, and performance cost, it denotes the particular pool of resources to hosted applications to maximize the performance utility. Power cost reduce the power consumption, and adaptations cost to minimize the minimum under the restrictions that VM CPU capacities for each request rate are given and static. We'll also see this. It's plotted between the power and time, and the previous between the response time and the times taken. Here the overall power consumption with the Mistral is lower than that of other approaches, because Mistral only uses a few hosts and perform less adaptations even at high request rate. We can see the curve of performance and power. It shows that using 4 hosts at crest request rates provide the optimal exchange between performance and power. However, the Mistral selects configuration with 2 or 3 hosts only, as the utilization cost for 4 hosts would be too high. Performance cost is forced to use 4 hosts when the both application request rates go high in order to host the VMs with essential VM CPU capacities. Yeah. From the research results of Yang Chu Lee and Zomaya, the data in the given tables and graphs obviously show that the competent energy save abilities of ECTC and MaxUtil. The overall MaxUtil and ECTC have performed better than the arbitrary algorithms, without considering the adoptions of the migrations by 18% and 13% respectively. While energy savings and high and random resources utilization patterns are still appealing, jobs with lesser utilization of the resources are more suitable for job association. The advantage of using migration was not clear. This primarily because migrated tasks have tendency to be short remaining processing times, and this task likely to obstruct the association of newly incoming jobs, which results in more energy consumption when compared to that case of migration is not considered. So these are the graphs. This plotted between the energy consumption and the number of jobs. This yellow color graph indicates the MaxUtil, and the ECTC is indicated with this triangle graph. So these are the tables with the ECTC and MaxUtil. The migration, energy savings, and the average percent of are calculated with high and low indications. So in this comparative study with Akash Verma, in his work done, we can notice that the application has a dynamic power range around 75 watts, and that can be utilized by a situation or capping methods. Additionally, we can notice that the power model of every application is distinctive, with HPL1 indicating solid non-linearity. This non-linearity can be used for power saving and optimization by load unbalancing using a workload manager, which loads a server to full utilization between loading any other server. The power drawn based on the two servers with workload manager, it would be approximately 187 watts and 158 watts respectively, and a total of 345 watts as shown in the graphs. Yeah, in the below graph it's plotted between power and the CPU utilization. Yeah, we can see that the total of 345 watts is used from the graphs, and similarly we can note the effects of increasing memory footprint. Here the graph is plotted between power and memory used. We observe that the HPC application does not appear to disturb the power utilization by the server. In beginning it may seem that it's a contradiction to that power drawn and utilization depends on memory bandwidth drawn by the application, but we can see that the memory footprint does not regulate the memory bandwidth or total pages of memory touched by the application per unit time. And from this graph we can see that it's plotted between the total kilowatt hours and the total number of hours, and this pink color line indicates it using with green cloud, and the blue color line indicates with without using the green cloud. We can see that the green cloud using with the green cloud, utilization power is much more better than the without green cloud utilization. And we can observe here that from from the starting, it rises, the green cloud utilization task rises, and in the it rises and goes to the top at the 7th hour, and coming to the end till the 12th hour it again goes down. This happens. So here, green cloud, we used 4 servers so that the energy consumption is still lower than no green cloud is used. So it's worth noting that the time regulation used green cloud, there will be no interruption to the service running on the cloud computing platform. So we'll reach the conclusion. So I'll conclude by saying that the effective and effective usage of power resources in the cloud services can benefit in achieving green cloud computing. So we have discussed about the different works done by the researchers for utilization of the effective utilization of the cloud resources, and thus encouraging the green cloud computing and helping our environment. So some researchers presented with power saving models for calculating cost and expense of the cloud services. Some work focus on virtualization, which is a primary methodology for energy reduction of cloud services. Few works focused on presenting a new distributed system architecture to perform dynamic VM association to reduce the energy consumption in the data centers, while few other focused on improving green energy used by modeling a data center, which this is continuous power supply from the wind renewables. Also, we compare different values when power consumption plotted with time, so implementing effective methods in reducing the power consumption and increasing the effective utilization of servers in the data centers. These together can help in achieving green cloud computing. I have also mentioned some references here. You also could refer that and see the what the effective usages of green cloud computing in the cloud areas. So thank you.